And my function h will be x, let's say it's x squared plus y squared. Right? All of a sudden, I've made a pretty complicated boundary condition. If you're going to solve that, even if you had a nice domain, right, using finite difference, I've just given you something that's a pain to deal with. Okay? Not trying to be mean. We're going to talk about that in a minute. So right now, let's just go and say, OK, that's my boundary. So that red one I changed. But by the way, the default on all these boundaries is that u is equal to 0 on the boundary. Right? That was the default that I had. Let's go to another one over here. Let's take that one. I'm going to pull this out. Come on, here we go. Let's switch to Neumann. Neumann, you get to impose the derivative conditions across the boundary. And here it is. N is the normal. So whatever the normal direction is, basically dotted with c times gradient of u. Okay, so this is basically, this here is like calculating the normal direction for u, plus q, u equals g. Q right now and g are both 0. So right now what it's imposing is the gradient across the boundary is 0. Okay? So the flux across that boundary. Basically, c is the direction vector. It gives you the normal to. So you don't get to change with n and c. This is just saying I can figure out which way it's pointing across the boundary. Yeah. So q and g are generically 0 under the Neumann. Again, so it's like saying, like in a very simple case would be, you know, if you have a one-dimensional PDE, it'd be like saying u of x equals to 0 on the boundary. That's the default. Here we can say, well, how about I make it equal to, again, you can make it any function of x and y you want. I'll make it just constant, 10. The flux across there is 10. I don't know, let's make q something like x cubed. I'm just making stuff up. I can do anything in this. I don't even have to think about it. Someone else is thinking about it. Right? I mean, that's the idea. This is why you pay money for these codes, right? It's like you could focus in on the science you want to do instead of having to write, thinking about, geez, do I want to make it that complicated a function? What's it going to mean in terms of building my x equal to b? You don't even care. At this point, you don't care. You just put in any function I want. Okay? It's like having someone's credit card. That's not yours. Okay? Oh, look at that. Changed to blue. Do you see that? Blue, Neumann. Okay? Derivative conditions. Red, just constraint, Dirichlet, which is a constraint directly on u itself. Okay? All right. What do you think so far? So well, you can kind of. Well, no. You're like a mixed. Well, effectively, if you look at the Neumann, you do have the ability to have both, right? Because if you look at the, let's go back to here. If you look at the Neumann, you really do have both here, right? You have a derivative of u plus u. You can always, in other words, by turning q to 0, you just have a derivative. If you want just u by itself, you go use your Dirichlet. And if you want both, you have both right there. What's u? What's u? U is your solution. U is the field it's going to solve for on this domain. U could be whatever. So for instance, for us, U is the vorticity or the heat equation, whatever we want, whatever our quantity of interest is that we're solving for. You're going to have to solve a PDE here for a quantity U. Okay? Okay. There we go. There's our boundaries. Look at that. That's kind of it. You just click on all the boundaries you want, impose some boundary conditions. You've got your domain. You got your boundary conditions. Yeah.
Arrows tell us anything?
Good question. I don't think so. But please don't quote me on that. I don't think so. I think, yeah. It's never meant anything to me, at least. It could mean something to somebody else. Well, so what happens is, yeah, here, it could be that you're going to have some interesting issues at that boundary, right? Because you're having to impose one here, and what it does is tries to do the best matching of what it can do. Doesn't criticize you. No. No, that's a great thing. You know, MATLAB never criticizes you. I mean, unless you think dimension arrays do not match. If you think that's criticism, then man, is this a jerk, right? We call that friendly help. All right. That's the number one error. Is that everybody's number one error? All quarter long? Dimensions don't agree? No. You should just tape it on your machine and just have it memorized there. All right. So moving left to right. So draw the stuff. Boundaries. Notice the order, right? You put the boundary down. You specify the boundary conditions first. Most of the time when we teach a PDE course, we always talk about, oh, here's the PDE. This is what's important. There's a certain philosophical view here that says, actually, what drives most the physics or the dynamics in a lot of systems is the boundary itself. Okay? And this is really important to be thinking about, is that the boundary conditions are as important as your PDE. And here, it's kind of placed like you're placing these boundary conditions first. Now we get to the PDE.